welcome to this video. Today I am going to explain two important image processing techniques in OpenCV, counter analysis and blob reduction. Before we move to the programs, let's first understand what these techniques are. Counter analysis is used to detect the boundary or outline of an object. Once the boundary is detected, we can calculate the important properties such as area, perimeter, and bounding box. Blob reduction is used to detect connected regions in an image that have similar brightness or intensity. These connected regions are called blobs. These two techniques are widely used in applications like medical imaging, industrial inspections, object detections, and robotics. In this program, we will first explain the basic concept using presentation. Then we will understand both Python programs line by line, execute them, and finally analyze the outputs. Now, let's see how counter analysis is performed. First, we load the input image using readout function. Then the image is converted into grayscale because counter reductions only require intensity values and not color informations. Now, we apply the thresholding, which converts the grayscale image into a binary image. This makes the object and the background easier to separate. After that, the fine counters of detect the boundaries of all image present in the image. Finally, draw counters of draws those boundaries. And OpenCV calculates important properties such as area, perimeter, and bounding box for each counter. Now, let's look at the important features or counter analysis. A counter analysis is simple, the outlier or boundary of an object. The area represents the total space occupied by the object. The perimeter represents the total length of the object. The bounding rectangle is the smallest rectangle that completely surrounds the detected object. You might have seen a rectangle drawn around the detected face. This is the common example of bounding rectangle. These features help us understanding the shapes and size of the object, which is why counter analysis is used in applications like shape recognitions, quality inspection, and medical image analysis. Now let's move on to the blob reduction. A blob reduction is a connected region of pixels that has similar brightness or intensity. First, we load the image in grayscale, then we calculate the simple blob reductor parameters and set filters such as area, circularity, convexity, and inertia ratio. After configuring this parameter, we create the detector and scan the image to identify the blobs. Finally, draw key points of makes every reduction blobs with a circle, showing both its location and approximate size. Now, let us understand the filters using blob reductions. The area filter detects blobs only with a specified size range. The circularity filter helps identifying objects that are close to circle shape, making it useful for detecting objects like coin or table. The convexity filter removes irregular objects with deep indentations, while the inertia ratio helps determine whether the blob is elongated or nearly circular. Using these filters together improve the accuracy of blob reductions and remove the unwanted regions. Finally, let us summarize the difference between counter analysis and blob reduction. Counter analysis focus on detecting the boundary of an object and calculating the properties such as area, perimeter, bounding box. In contrast, blob reduction focus on identifying the connected regions based on brightness or intensity and provides their location and size. In simple words, if we want to analyze this object shape, we use counter analysis. If we want to detect a bright or connected regions, we use blob reduction. Both techniques are widely used in computer visions because they help extract useful information from the image quickly and accurately. So, we have understood the basic concept of both counter analysis and blob reduction. Now, let's move to the Python program and understand how each step is implemented. After that, we will execute both programs and analyze the outputs. Now, let's move to the counter analysis program. First, I import the OpenCV library which provides the functions required for the image processing. Next, I load the input image and check whether it has been loaded successfully. If the image is not found, the program displays an error message. After that, image is converted to grayscale because counter reduction is works based on pixel intensity values, not rather than color information. Then Thresholding is applied to convert the grayscale image into a binary image. This helps separate the object from the background, making counter detection easier. Next, the program detects the counter present in the binary image and stores them. After detecting the counters, a copy of the original image is created and all detected counters are drawn on it using green color. The program then calculates the important properties such as area, perimeter, and bounding box for each detected counters and prints the values in the terminal. Finally, the original image and the counter output are resized for better viewing. Now, let us run the program and observe the output. Here, the second window shows the original image and the first window shows the counter detection result. We can clearly see the green lines representing the boundary of the detected object. Since this image contains many small details, OpenCV has detected a large number of counters. In the terminal, the area, perimeter, and bounding box values for each counter are displayed. This confirms that the program has successfully detected and analyzed the counters in the image. Now, let's move to the blob detection program. First, I import the required libraries and load the input image. The program also checks whether the image has been loaded successfully. Next, the image is converted to grayscale because blob detection is based on pixel brightness. After that, I create a simple blob detector parameter. In this program, the area filter is enabled so that blobs are detected only within the specific size range. The circularity, convexity, and inertia filters are disabled, allowing blobs of different shapes to be detected. Once the parameters are configured, the blob detector is created and the program scans the image to detect all the blobs. The total number of detected blobs is printed in the terminal, and the detected blobs are marked on the image using red circles. Finally, the original image and the blob detection result are resized for better reviewing. Now, let's run the program and observe the output. Here, the first window shows the original image and the second window displays the blob detector result. The red circle indicates the dedicated blobs. In the terminal, we can see that the total number of 307 blobs have been detected. Each red circle represents a connected region with a small brightness or intensity. This confirms that the program has successfully detected the blob present in the image. In this video, we learned how counter analysis and blob detection work using OpenCV. We understood the basic concept, explained the Python program step by step, and observed the outputs generated by both techniques. Counter analysis helps us identifying the boundaries and shape related features of object, while blob detection helps us identify connected regions based on pixel intensity. These techniques plays an important role in many real-world computer vision applications such as object detection, medical imaging, robotics, and industrial inspections. Thank you for watching. I hope you found this video useful.